This lesson is on Riemann sums for quadratic functions. So our first example is the integral from 0 to 3 of x squared minus 2x plus 4 dx. Now what does that mean? That means we want to find the area under the curve on the interval as x goes from 0 to 3. So here is the function x squared minus 2x plus 4. X starts at 0 and it goes to 3. This integral represents this area. Now we don't have any geometry that will enable us to do this. The best we can do in the beginning is to approximate. So I'm going to suggest that we use 6 rectangles to approximate, and I always like to use right endpoints. So our interval goes from 0 to 3. If we're going to use 6 rectangles, how wide will each rectangle be? Well, from 0 to 3, the width is 3, but we're subdividing that into 6 pieces. So each rectangle will have a width of 1/2. So let's visualize that using, again, right endpoints for the height. So here's the first rectangle. It goes up to 1/2. That's how high it goes, and it shoots over. So this is the first rectangle. Second rectangle also has width of 1/2, up to the function f of 1. We find the area of this rectangle. Third one out to 1.5. Notice now we're above the graph. Fourth one up to f of 2, measure that. Fifth one out to 2.5, measure that. Sixth one out to 3, measure that. So if I add the areas of those 6 rectangles, that should give me an approximation for this area here. Now it's not going to be a very good approximation. You can see we overshoot here. We undershoot here. It appears to me as if our approximation will be a little bit too large, but at least it'll give us an idea approximately what that area is going to be. In general, the integral from a to b of f of x dx, that represents the area under the curve on the interval from a to b. That width will be b minus a, that's the width of the interval, divided by n, divided by the number of rectangles you're using. So here we have 6 rectangles, b is 3, a is 0, 3 minus 0 divided by 6 rectangles. The width is 1/2. So it'll be nice to remember that when we're setting up these rectangles, larger endpoint minus smaller endpoint divided by n will give us the width of each rectangle. So here's what we're working with. There's our function, and there are the 6 rectangles. The function f of x is the x squared minus 2x plus 4 we are looking to examine. Now, what is the height of the first rectangle? Well, I am using right-hand endpoints. So the right-hand endpoint on the first rectangle occurs at 0.5. So the height of the first rectangle is the value of the function at 0.5, f of 0.5. So that's the f of 1/2 is the height of the first rectangle. The height of the second rectangle, notice the right endpoint is 1, would be f of 1. Height of the third rectangle, f of 1.5, or f of 3/2. Fourth rectangle here, the height of the fourth rectangle, it's f of 2. Height of the fifth rectangle, f of 2.5, or f of 5/2. And the sixth rectangle is f of 3, is the height there. So, and how about the width? We have all these heights, fine, plugging in those numbers into that function. The widths are all the same. The widths of these rectangles are all equal to 1/2. So the width is 1/2, and the height changes depending on which rectangle we're studying. So I want to make a table of values that's going to look at what again? Every width is 1/2. b minus a over n, 3 minus 0 over 6. The width of each of these rectangles is 1/2. Original width is 3 divided into 6 pieces. Each rectangle is 1/2. Rectangle 1, his height is f of 1/2. Rectangle 2, f of 1. Rectangle 3, f of 1.5. Rectangle 4, f of 2. Rectangle 5, f of 1/2. F of 6, f of 3. So we have all of those heights. Now we need to find out what those heights are, so I've got to plug those into the function to see what we get. 1/2 squared is 1/4. 2 times 1/2 is 1. So 1/4 minus 1 plus 4. What does that give me? 3 1/4. 1 squared is 1, minus 2 times 1 is 2, 1 minus 2 plus 4 gives me 3, etc. So I have the heights for all 6 rectangles. But my goal is to approximate the area under the curve. So I've got to have the area of each rectangle. Now what is the area? Area is the width times the height. So the area of rectangle 1 is 1/2 times 3.25. Area of rectangle 2, 1/2 times 3. Area of rectangle 3, 1/2 times 3.25. Area of rectangle 4, 1/2 times 4. Area of rectangle 5, 1/2 times 5.25. Area of rectangle 6, 1/2 times 7. So let's go ahead and do all those. So we'll make another column which will be areas. You'll notice that rectangle 1 and rectangle 3 are the same. They have the same width and the same height, so of course they have the same area. Kind of interesting. The total area is what approximates this integral, approximates the area under that curve. Remember what we are trying to do. We are trying to approximate this area under the curve. So we're drawing all 6 of those rectangles. Here's 1, here's 1, here's 1. You get the idea. So we want to approximate that area in pink. We are using all of these 6 rectangles to approximate that. So to approximate that, I'm going to add up those 6 areas, and what do I get? I get 12.875. But I believe that that's probably too big, just looking at the geometry. Rectangle 6 is much bigger than it would be the area under the red curve. Rectangle 5, much bigger. Rectangle 4, much bigger. Rectangle 3, a little bit bigger. Rectangle 2, a little shorter than it should be. Rectangle 1, a little shorter than it should be. But on average, it looks to me like this is an over-approximation. Now, how can I get a better approximation? I use just 6 rectangles. Well, I could use a whole lot more rectangles. And with spreadsheets, the computation's not too difficult. So for my second approximation, I said, let's use 100 rectangles and write endpoints. So what will 100 rectangles and write endpoints look like? Well, interval from 0 to 3, that's 3 wide. We're breaking it into 100 pieces. So the width of each rectangle is 3 minus 0 divided by 100, or 0.03. So my first rectangle goes over 0.03. Next one over 0.06. Next one over 0.09 as we move across. Now, is there a way for me to talk about that? So the widths are all 0.03, but let's think about this. 0.03 times 1, then 0.03 times 2, then 0.03 times 3. And this last one is 0.03 times 100. So in terms of setting up our table, what are we going to have? I have 100 rectangles. The widths are all 0.03. First one, 0.03 times 1, 0.03 times 2, 0.03 times 3, 0.03 times 4, 0.03 times 100, which is 3. So I evaluate the function at each of those 100 points. Now that's going to be a lot of work to do, but again, with the spreadsheet, it's not terribly difficult. So using the right endpoints, again, notice this height is the value of the function at 0.03. This height for rectangle 2 is the value of the function at 0.06. Rectangle 3, the height is the value of the function at 0.09. Rectangle 100, the height is the value of the function at 3. So I take width times height to get the area, and I have those 100 numbers. Now this should be a better approximation than my first example, but I don't expect it to be perfect. What do I get? I get a total area of 12.04545. Now what did that compare to my first approximation? We had 12.875. So I assume my 12.045 that I have this time is a better approximation. It's getting a little bit closer. I can't be sure if this is a little too high or a little too small, but this is what we'll start with. Now, where do we go from here? Well, now I want to examine n rectangles and write endpoints. N rectangles, and will change and will grow. But for the sake of our discussion, let's say we're working off of n rectangles. Now, 0 to 3, that width is 3. I want to break it up into n equal pieces. So our width will be b minus a over n in general. In this case, 3 minus 0 over n, or 3 over n. So each rectangle I have is going to have the same width of 3 over n. Looking at that picture, my first rectangle goes out to 3 over n. Next one to 6 over n. Next one to 9 over n. By the time I get to the nth one, we're at 3. Now, something to think about. 3 over n is 3 over n times 1. 6 over n is 3 over n times 2. 9 over n is 3 over n times 3. 3 is 3 over n times n. So you see the right-hand endpoint is just 3 over n times whatever that little number is. So notice the first one, 3 over n times 1, then 3 over n times 2, then 3 over n times 3, 3 over n times 4, 3 over n times 5, etc., until I end at 3 over n times n, which is the same as 3. Widths are all the same. Widths are all 3 over n, but what are the heights? What's the height of the first one? F of 3 over n times 1. What's the height of the second one? F of 3 over n times 2. What's the height of the third one? F of 3 over n times 3. What's the height of the last one? F of 3 over n times n. So we have the widths, we have the heights, we multiply those together to get the areas. So here we go. Notice I have n rectangles. Widths are all 3 over n. Height f of 3 over n times 1, f of 3 over n times 2, f of 3 over n times 3, f of 3 over n times 4, ending at f of 3 over n times n. Area is width times height, so 3 over n times f of 3 over n times 1, etc. Remember what f is? F is our function. What's our function? X squared minus 2x plus 4. So what we're going to have to do next is figure out some way to look at the total area, right? The total area requires me to add up these 100 or n items. In this case, we 100 our last example. So 3 over n times f of 3 over n times 1 plus 3 over n times f of 3 over n times 2 all the way down to 3 over n times f of 3 over n times n. So there's our total area, adding all n pieces up. What is my next move here? To recognize that each of these pieces is multiplied by 3 over n. So I can factor out the 3 over n. Take the 3 over n out and multiply a big bracket. So notice what I've done. 3 over n times f of 3 over n times 1 plus f of 3 over n times 2 plus f of 3 over n times 3 plus f of 3 over n times 4 plus dot 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 plus f of 3 over n times n. This is a sum. I is changing. 1, 2, 3, 4, n. It's the sum as I goes from 1 to n of f of 3 over n times I. There's our notation. When I is 1, f of 3 over n times 1. Kick it up, f of 3 over n times 2. Kick it up, f of 3 over n times 3. When does it end? It ends at n. So this is a relatively simple way for us to describe that total area for n rectangles. Now what do we need to know? Well, what's f of x? We started with this integral from 0 to 3 of x squared minus 2x plus 4. So this tells me what my function is. My function f of x is x squared minus 2x plus 4. So I've got to plug this thing, this 3 over n times I, into f to get that to work. So what do I have next? I have f of, again, 3 over n times I is the same as 3i over n. Square the first piece, 3i over n squared minus 2 times that piece, minus 2 times 3i over n plus 4. So that is f of 3 over n times I. Let's simplify the algebra. What do we get? Well, we get this first. We're going to sum all those guys. So the sum, 3 over n times, there's my function, f of 3 over n times I. 3i over n squared minus 2 times 3i over n plus 4. Next, the integral is the limit as n goes to infinity. We have n rectangles currently. We want n to go to infinity. So I need the limit as n goes to infinity of all of this. That will be our area under the curve. That will give us that pink area that we started with in our first example, right? The limit as n goes to infinity will give us this area under the curve. That's what we're looking for. So let's go ahead and do that analysis. So we've got to do some algebra. What's next? 3i over n squared, 9i squared over n squared. 2 times 3i over n, 6i over n plus 4. Next up, the sum of each of these three pieces is the sum of the first piece minus the sum of the second piece plus the sum of the third piece. So we think in a sense of the summation sort of distributing, behaving kind of like that. The sum of the sum is the sum of the sums. So this is where we are currently. Now I is changing, so 9 over n squared is not changing. That can come out in front of the sign, the sigma notation. I is changing, 6 over n is not. That can come out in front. So notice what I have. Pulling the 9 over n squared, I have 9 over n squared times the sum as I goes from 1 to n of I squared. Minus pull the 6 over n out, sum as I goes from 1 to n of I, and then just leave the sum as I goes from 1 to n of 4 alone. And then we could multiply in that 3 over n. So notice 3 over n times 9 over n squared, 27 over n cubed. 3 over n times 6 over n is 18 over n squared. 3 over n times 1, 3 over n. Lots of algebra, yes. Now we need to know these rules. What is the sum as I goes from 1 to n of I squared? What is the sum as I goes from 1 to n of I? What is the sum as I goes from 1 to n of 4? Now the easiest one is the sum as I goes from 1 to n of 4, which is 4 plus 4 plus 4 plus 4 plus 4 n times. I hope that's obvious that that's 4n. So this gets replaced with 4n. Now, the sum as I goes from 1 to n of I is not obvious, but here's the fact. The sum as I goes from 1 to n of I is a half n squared plus a half n. Relatively easy to prove with math induction or something like that. But you can go ahead and accept that. So that is going to replace the sum as I goes from 1 to n of I, the half n squared plus a half n. And finally, I need something that represents the sum as I goes from 1 to n of I squared, which is a third n cubed plus a half n squared plus a sixth n. That's going to replace that. And once we do all of those, the algebra is just about finished. So this is our last line, and now we're going to go ahead and make our substitutions. Notice the sum as I goes from 1 to n of I squared is substituted here. The sum as I goes from 1 to n of I is substituted here. The sum as I goes from 1 to n of 4, 4n is substituted there. Next, distribute, be careful. 27 over n cubed times the third n cubed is 9. 27 over n cubed times a half n squared, 27 over 2 times 1 over n. 27 over n cubed times 1/6 n, 27 over 6 times 1 over n squared. Similarly, for the 18 over n squared times a half n squared is minus 18. Minus 9 over n, and 3 over n times 4n is plus 12. So look at that algebra. I hope you're with me in terms of how that's done. Distributing this multiplier out in front, boom, boom, boom. I left the minus sign and I distributed positive 18 over n squared here and here. And then 3 over 4n times 4n is just going to give me 12. Now, as n goes to infinity, 27 over 2n goes to 0. If n is a million, 27 over 2 million, basically 0. If n is a million, 27 over 6 times a million squared, basically 0. 9 over a million, basically 0. So we get all of that, which gives me an answer of what? Gives me an answer of 12. So what we're claiming is we are claiming that that pink area is 12. Now, what did we say before? What were our approximations that we had? If I recall, first approximation I had was 12.875 for 6 rectangles. Not a very good approximation, but it was at least in the neighborhood. For 100 rectangles, we had 12.04545. If we wanted a better approximation, we'd use 1,000 rectangles. But using the limit as n goes to infinity, using our calculus, we go ahead and get our answer of 12. So 12 is the area under the curve that we're able to get by looking at that area as a limit of a Riemann sum. So let's look at one more example. This time I want to look at the limit from 1 to 3 of 10 minus x squared. This is a little harder because it's not starting at 0. So here's our picture. Starting at 1, going to 3, 10 minus x squared, we want to get this pink area. What are we going to do? Well, let's jump immediately to our n rectangle approach. So I want to have n rectangles. We're going to use right endpoints. That's my preferred strategy. And then we are going to take the limit as n goes to infinity eventually. Now, what is my width? The width here from 1 to 3 is 2. We're breaking it up into n equal rectangles, so it will be 2 divided by n, or b minus a, 3 minus 1, over n. 2 over n, n is the width of each rectangle. So, 2 over n here, 2 over n here, 2 over n here. So there we go. I have n rectangles. Rectangle 1, rectangle 2, rectangle 3, all the way out to rectangle n. Each width is 2 over n. But notice we started at 1, so this first right endpoint is not 2 over n, it's 1 plus 2 over n. The second endpoint is 1 plus 2 over n plus another 2 over n. This third rectangle is 1 plus 2 over n plus 2 over n plus 2 over n. This last endpoint is 1 plus 2 over n times n. 1 plus 2 or 3. So we want to use the right endpoints. We want to see what those endpoints are. So let me go ahead and carefully demonstrate that. So 1 plus 2 over n times 1, 1 plus 2 over n times 2, 1 plus 2 over n times 3, ending at 1 plus 2 over n times n. That's what we want. That's what we're going to try to get. Each width is 2 over n. So we make our table. Width times height. The height of this first rectangle, f, of 1 plus 2 over n times 1. The height of the second rectangle, f, of 1 plus 2 over n times 2. Height of the third rectangle, f, of 1 plus 2 over n times 3. Height of the fourth rectangle, f, of 1 plus 2 over n times 4. Height of the nth rectangle, f, of 1 plus 2 over n times n. But notice that simplifies to 3. 2 over n times n is 2, 1 plus 2 is 3. So the nth rectangle, indeed, the height is f of 3. The area of all these guys is width times height, so 2 over n times f of 1 plus 2 over n times 1, 2 over n times f of 1 plus 2 over n times 2, etc., all the way down. So, if I want to get the total area of n rectangles, I've got to add all of these up. Add up n of them. So the total area of n rectangles, 2 over n times this right endpoint plus 2 over n times that function of that right endpoint all the way to the end. And you will notice there is a 2 over n in each one. So we're going to factor out that 2 over n. And then you want to notice what's changing here. 1, 2, 3, 4, dot, 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 ending at n. So I can do this as f of 1 plus 2 over n times I, summing as I goes from 1 to n. So rewriting this in sigma notation, we get 2 over n times the sum as I goes from 1 to n of f of 1 plus 2I over n. That's what we're dealing with. Now, what was our function? Do you remember what our function was? We started with this. Integral from 1 to 3 of 10 minus x squared. So the function we're dealing with, f of x, is 10 minus x squared. So I need to plug this 1 plus 2I over n in for x and take 10 minus x squared. So 10 minus x squared, 10 minus x replaced with 1 plus 2I over n. That's our total area for n rectangles. And the way we're going to get the actual area, we'll take the limit as n goes to infinity of the total area for n rectangles. So let's see what happens here. So now we are back into a challenging area of algebra. Well, 1 plus 2I over n squared, that's what? 1 plus 4I over n plus 4I squared over n squared. 10 minus 1 is 9, and then minus 4I over n, and minus 4I squared over n squared. Now I have the sum of a sum, or difference, so sum of 9 minus sum of 4I over n minus sum of 4I squared over n squared. So in a sense, we think of distributing the sigma notation, but in reality, the sum of a sum is the sum of a sum. So sum of this piece minus sum of that piece minus sum of that piece. Don't forget the 2 over n. Now, I is changing. 4 over n is not 4 over n, can come out in front, multiply the 2 over n. 4 over n squared can come out and multiply the 2 over n. What does that give us? 4 over n times 2 over n is 8 over n squared. 4 over n squared times 2 over n is 8 over n cubed. And we're almost finished. So we need to figure out what is the sum as I goes from 1 to n of I, what is the sum as I goes from 1 to n of I squared, what is the sum as I goes from 1 to n of 9. So, I mean, these are things that we looked at before. Sum as I goes from 1 to n of 9. 9 plus 9 plus 9 plus 9 plus 9 plus 9 is 9n. Sum as I goes from 1 to n of I. What do we say that was? A half n squared plus a half n. Sum as I goes from 1 to n of I squared was what? A third n cubed plus a half n squared plus a sixth n. So here's our current total of n rectangles. So now we still have to fight through the algebra a little bit. 2 over n times 9n is just 9. And then where did we go from there? This time I did distribute the negative. Minus 8 over a half, 8 times a half minus 4, n squared over n squared minus 4. 8 over 2 is 4, so minus 4n over n squared over n. Minus 8 over n cubed times the third n cubed. The n cubes would cancel, minus 8 thirds. Minus 8 over n cubed times the half n squared, it'd be minus 4 over n. Minus 8 over n cubed times the sixth n minus 8 sixths with an n squared downstairs. So this is our current total of having n rectangles, But the integral, the area under the curve, is the limit as n goes to infinity of the area of n rectangles. So what will that be? The limit as n goes to infinity of all of this. Well, 4 over n goes to 0, 4 over n goes to 0, 8 over 6n squared goes to 0. So we get 18 minus 4 minus 0 minus 8 thirds minus 0 minus 0, which gives me an answer of 34 thirds. That is what we believe the area under the curve is from 1 to 3 of 10 minus x squared. So what is that? That's a little bit more than 11. Does that seem reasonable? If we go back to our picture, let's count 1, 2, because this width is 1, height is 1. So each one of these rectangles is really area 1. 1, 2, 3, 4, 5, 6, not quite 7. Maybe these two guys are 8, 9, 10. Maybe these two guys are 11-ish. So we're in the neighborhood at least. We're saying 11 and a third is what we think the area is. So kind of by eyeballing it, you ask yourself, does your answer seem reasonable? And I would argue that it does. That our answer of 11 and a third is pretty close to what we would get when we tried to eyeball this and try to approximate it there. All right, that will conclude this lesson.